Hi, and welcome to the fourth episode of the Sienna training series. I'm Rodrigo Enriquez, and I will be showing how the Sienna Dyn and power simulation dynamics works. As discussed in previous episodes, Sienna is an open source ecosystem for power systems modeling, simulation, and optimization. In these episodes, we will focus on how Sienna Dyn works. In particular, we will focus in the power simulation dynamics package on how to run a time domain simulation and a brief explanation on what is happening under the hood. Link to the Julia packages and documentations are available in the video description. This is the fourth episode of this Sienna tutorial series. Episode 2 is relevant for the episode of today, so be sure to check that out, since Sienna data is directly used to handle the system that Sienna Dyn uses. We will primarily focus on the power simulation dynamics, as I was mentioning, package. So this is the environment that we will be using in Julia for this session. All of the previous packages are listed here, but in addition, some tiles and ordinary DFQ are packages that contains the solvers that will be used for time domain integration, while Plotly.js is the software, the package that we will use to display the result from power simulation dynamics. The fundamental pipeline for using Sienna Dyn is as follows. Use powersystem.jl to load data into a system in memory. This data can come from raw and DYR files, for example, as in PSCC, or you can directly use powersystem.jl to create your own systems. Use power simulation dynamics and internally powerflows.jl to initialize the system, construct the states, obtain the Jacobian, and other required structures that are useful for running a simulation. And finally, you can run using power simulation dynamics a small signal analysis or a time domain simulation as required for you. So in the following demo, we will showcase the following. Basically, we will use powersystem.jl, the system functions, to construct a system in Julia using raw and DYR files. We will run a power flow to showcase the power flow solution based on the original static data. We'll use power simulation dynamics to create a branch trip to specify a perturbation for the time domain simulation. Also use power simulation dynamics simulation function to construct a dynamic model and initialize the system in the specified operating point that comes from the original data. And we will perform a small signal analysis and a summary of the eigenvalues to explore this small signal result before the branch trip. And finally, we will run using the execute function, a time domain simulation, plot some of the results using Plotly.js. So here is the script that I will be using for today. All of these scripts are available in the video description. So first we will activate our environment that we previously specified in the presentation. Here we're loading the packages used in this tutorial, and then we will load using power systems, the system that come from the raw and DYR data that is available here, also available in the description of the video. For example, this system has two generators, one that is more as a classic generator, Gen CLS, and a hen row model. In doing that, we load the system, and power systems display some of the information of the system that we just load. Then we will run a power flow that returns the results in a dictionary. And for example, these are the bus results coming from this 3-bus system. And we can see some of the information such as the voltage and the power flows. Then to create a branch trip, as I was mentioning, we require the name of the branch. We can use show components in power systems to list all the names, and we will create a branch trip here, as mentioned, at 1 second between bus 1 and bus 2, using the full name that is displayed here. Running this, we create the branch trip. Then most of the systems comes using constant power load models. So many of the dynamic simulations use constant impedance. So we will use this for loop to go through each of the loads available in the system and transform them to constant impedance. And then using the simulation function, we will create or initialize the simulation using a residual model for the system that we define in the specified folder here for 20 seconds simulation using the branch trip that we defined before. So if we run these, they give us a summary of the number of states, number of perturbation, the time span, and plenty of that information. Before running and executing the branch trip, we'll perform a small scene analysis for the operating point. And if we run that, it basically return that is a small signal stable, and we can get a summary of the different eigenvalues using the summary eigenvalues function that display for all of the 6 eigenvalues, which one is the most associated state with the respective participation factor, the real and the imaginary part of that eigenvalue with the damping and the frequency associated to that. For example, we can see here that the first eigenvalue with this real part has the rotor flux as a more associated state. With that, we're now set up to run a simulation using the execute command and using the IDA solver from Sundials. Running that, we see that the simulation completed. We load the results, and then we can use this function get voltage magnitude to get the voltage at different buses, or we can use the get state series to get a specific state. For example, here I'm getting the rotor speed from the generator 102. So if I run this, I will obtain those results, and these the specific results. And finally, using Plotly AES, we can get the results here, for example, for the bus, for the voltage at bus 102. This is the response. Since this example doesn't have any excitation system, the voltage does not recover after the branch trip. Similarly, for the rotor speed, we see that since it's a branch trip, at the end it returns to the nominal rotor speed. And that's it. Thank you for your attention, and be sure to check all the links in the description for more information about Sienna.